All right, our science class, let's go over Chapter 20, Global Climate Change. Our climate is really dynamic and complex. It's a multi-dimensional system with a lot of interacting parts. We've got our atmosphere, our hydrosphere, meaning all the oceans, rivers, lakes, the geosphere, biosphere, cryosphere, which includes snow, glaciers, ice, and frozen ground. All these moving parts are kind of interacting with one another, and when one of those component changes, it reacts and begins to change the other ones. And so that's why it's difficult to predict what will happen with climate because of all the interacting parts. Just an example of how complex our climate system is, here are some of the relationships between the different spheres. The ocean interacts with the atmosphere, okay, with heat exchange, evaporation. A lot of the CO2 in the atmosphere can be absorbed by the ocean. The biosphere interacts with the atmosphere, all the microorganisms that live on the surface of the ocean. The amount of sea ice that's in the ocean affects the reflectivity, changes in atmospheric circulation, changes in solar inputs, or changes in cloud cover. The geosphere can come in if there are increases in volcanic eruptions. And then there's us. We're part of the biosphere. We're burning a lot of fossil fuels. That goes into the atmosphere. So there's just a number of ways our climate system can be altered by different things that are occurring on Earth. And so remember, climate is long-term. Your day-to-day weather, what's the outlook going to be like tomorrow, rain chance, highs and lows, that's your weather. Your climate is long-term. When we're thinking next 100 years, what's the overall composite weather going to be, or if there's any shift, or are we just kind of going in these small variations? That's detecting climate and understanding how that changes through time. And to get an idea of how to understand how climate can change in the future, we got to look at what's occurred in the past to understand perhaps what will happen in the future. So the way we look at climate in the past is by looking at fossils. Those are just one of the tools that we use. And as a result of looking at different lines of evidence, we've reconstructed our Earth's climate going back hundreds of millions of years. And so our Earth's climate can broadly be characterized as being warmer kind of than it is today, or an interglacial period called a greenhouse, or colder than it is today, which would be more of an ice house or an ice age. Our instrumental records only go back as far as those instruments were invented. So that only gives us about 150 years around of direct observable collected data. So the way we reconstruct past climate is the field of paleoclimatology, and they use something called proxy data. And proxy data is indirect evidence of climate change. And one example of this are to look at really old plants that have been around for a really long time. This is a bristlecone pine that you find in the American West. They're as old as 5,000 years old. And so we can look to these individual species of trees and look at specifically their growth rings to see a climate record of about 5,000 years, however old the tree is. One way we can detect climate change is to go through seafloor sediment. Seafloor sediment is a great place to collect data. There's a lot of organic remains, fossils that and limestone, like there's coral, ancient coral, that they can tell us what sea surface temperatures were like in the past, which is pretty amazing. Foraminifera are a type of organism that live in the upper sunlit layers of the ocean and also in sediment. Here's a scanning electron image of a foraminifera right here. And there are many different species. And different species live in different types of environments, warmer and cooler environments, so they can give us a clue as to you know, what the oceans were like in the past. If you find them in deeper sediment, that goes deeper into the past. And our ocean sediment goes back at most about 200 million years. So remember, the oceans are like the ultimate resting spot for sediment derived from continents. And so anytime the ocean basins just are collecting sediment from land, and that includes volcanic eruptions, ash and dust, so you can kind of look back and find previous volcanic eruptions or just major geologic events, the arrival and extinction of species that are fossilized in the sediment. So ocean sediment really gives up a lot of data, especially the past 200 million years. Another form of proxy data is looking at stable isotopes. Stable, we've talked about radioactive isotopes. Those are isotopes that are unstable and they radioactively decay. Stable isotopes aren't radioactive and don't decay. Okay, and so there are a lot of different isotopes in nature. You can look up, Google the chart of the nuclides, and it shows you all the different variations of all the elements that we're familiar with from the periodic table. And one such variation is in oxygen. Oxygen has a couple forms. The most common are oxygen 18 and oxygen 16. So what this means is oxygen 16 has 2 fewer neutrons than oxygen 18. And so that means that oxygen 16's mass is much lower, or lower by 2 atomic units. And that difference in mass will account for difference in chemical behavior. And so these two isotopes will fractionate from each other from processes like evaporation. Okay, so what happens is marine organisms, right, that create their shells out of calcium carbonate, right? Calcium carbonate is CaCO, oxygen 3. And so they're going to pull the oxygen, dissolve the oxygen directly from seawater. So depending on what time they existed or when they existed in geologic time, they're extracting the oxygen from the ocean. And so they'll take in those ratios, whatever those ratios may be, oxygen 18 to 16. Now this value varies, and it varies depending on the overall climate of Earth during the time that that organism created its shell. And the way that they vary is that during non-glacial periods or warmer periods, when you have evaporation, oxygen 16 is preferentially, because it's lighter, preferentially goes into the vapor phase over oxygen 18, which means that the water vapor has an enrichment in oxygen 16. Okay, and that's just because it has a lighter mass, and that's why it fractionates to the vapor phase more often than not in the water. So, but during warmer times, the water vapor will just condense, rain back on land, and that water will run off back into the ocean. So that ratio doesn't really change, meaning that the ratio is pretty low. So you have 18 over 16, and the ratio is low because there's a lot of 16 in the ocean. So if marine organisms are creating their shells in the ocean, this ratio is going to be pretty low when you measure those shells. However, in glacial periods, when the Earth is really cold, what happens is the same thing happens. You have evaporation, more oxygen 16 goes into the vapor phase, and that oxygen 16 then falls onto land as snow. And because it's much colder, you have the formation of ice sheets and glaciers and a lot of snowpack. And so what happens is that oxygen 16 begins to be like sequestered on land, or just it stays on land for a while, doesn't melt and go or run off and go right back into seawater. And so your glacial ice is enriched in oxygen 16 relative to oxygen 18. And then as a result, the remaining seawater then has a lot of oxygen 18 versus 16. So the 18 over 16 ratio is really high. And that's reflected in the organisms that exist during glacial times. They'll have a much higher ratio. So what that means is we can go back and look at ocean sediment. Let's say we look at 150 million years ago, and we find that these the fossils of organisms that create their shells out of calcium carbonate have really high ratios. Then that means that 150 million years ago, this is what the climate must have been like. It must have been a glacial period. And if, let's say, we look at other sediment with calcium carbonate shells, and they have really low ratios, then we can assume that it was a non-glacial period. And so this is what we mean by indirect evidence of climate change. We also have a really good record of glacial ice or ice cores. That represents about 200,000 years of direct climate history. We can, because ice or water is H2O, we can also look at the oxygen isotopic analysis of the oxygen in the water or in the ice. Carbon dioxide and methane bubbles are also trapped in the ice itself. You can also find dust, volcanic ash, and pollen. And so if we go to our major glacial ice fields on Earth, which a few remained in Greenland and Antarctica, we can drill down and pull out these huge cores. You can see them here. This is a refrigerator filled with them. And we can look at what the Earth's atmospheric composition was like in the past. And here's a little graph right there. Here's the temperature. For the past 10,000 years, we've had pretty stable temperatures here. But if we go further into the past, here was our last kind of glacial maximum, where it was much colder than it is today. Okay, so this is 40,000 years before present. It's from direct data. We can also look at tree rings. Like I mentioned before, when trees grow, their rings are added to them every single year, and the thickness and density of the rings reflect the environmental conditions. And so we have some old trees. Those bristlecone pines are 5,000 years old, so they'd have 5,000 of these rings. We don't have to chop down the whole tree. We can just drill in it and get a core of the tree and then count the rings in this fashion. So you can see here's the first ring, and then all of these rings surrounding kind of like the beginning of this tree's life were fairly good. It means the weather was very conducive to growth for this tree. Perhaps these were the lean years, the college years when you're surviving off mac and cheese and cup ramen, right? Very thin years. Those were environmentally unfriendly. Then you can see there's the thickness kind of varies in different rings. We can also look at fossil pollen. I don't know about you, but springtime, the pollen kind of gets to me. I'm scratching my eyes all the time. But plants do this all the time. Plants just broadcast spawn, all this stuff into the air. It goes everywhere. It covers your car. It covers the ground. And what happens is a lot of times, well, all the time really, this pollen floats around and then falls into lakes, as an example. And so that will deposit much like sediment. And then every year you have another deposition of pollen, another deposition of pollen. And then you can look at an area, let's say one of the lakes in Florida, for example, get a sediment record of the lake from the oldest on the bottom to the youngest on top, and look at how the pollen has changed throughout the years of deposition, right? And things can happen. There can be major changes. Like places can be uplifted. Like on the Colorado Plateau, that was uplifted from sea level to about 8,000 feet. And so you can definitely find out or look at, if you had a lake that had a long enough record of that times that uplift, you could see changes in elevation from vegetation that's more prone to sea level, growing at sea level, and other vegetation that's more prone to growing at high altitudes. We can also look at coral. Coral, they act as what we refer to them as paleothermometers. So through the oxygen isotopic analysis, we can find out direct sea surface temperatures at the time that the coral was growing. And then we can also look at historical dates, harvest dates, floods, and human migrations. Those can signal changes in climate. This is an SEM image of pollen. This is what goes up your nose and makes you sneeze or irritates your eyes. And this is an example of sea surface temperature from coral. Okay, so this is a record about 450 years from 1600 to 1950 when this coral lived on Earth. And you can see the temperature fluctuations from year to year. Oh God, they're both red. It doesn't make any sense. So sea surface temperatures have been fluctuating kind of up and down over the past 450 years. A small record. All right, what's the composition of our atmosphere? This is kind of review for you guys. It's mostly nitrogen, 78%, then oxygen, and then an honorable mention is carbon dioxide at 0.04%. But the reason why we mention it is because it does have a huge effect on global climate. We'll go into that. Well, right here, actually, the greenhouse effect. And so what happens is shorter wave solar radiation passes through our atmosphere and heats up our Earth. You can feel this if you go outside and stand in the sun. You're going to feel warmer. And then as that short wave radiation hits our bodies and hits the ground, it's re-radiated and emitted by the Earth itself back into the atmosphere. And that long wave radiation or infrared radiation is absorbed by specific molecules, and carbon dioxide is one of them. Water vapor is also a greenhouse gas that traps long wave radiation. And so when it traps that long wave radiation, it re-radiates it back towards the Earth instead of allowing it to kind of go back into space. And so that selective absorption and reheating is what we call the greenhouse effect. Here's an example. I've shown you this before. The moon has no atmosphere, so shortwave radiation comes in, bounces right off, goes out into space. No collection of heat. That's why it's so cold here. Earth's in a balance. Okay, we do have some greenhouse gases, so incoming shortwave converted to long wave radiation. Some of this gets trapped by our atmospheric greenhouse gases and is re-radiated back to Earth, which keeps us warm or warmer. Okay, Venus is the other extent to this, like the other end member. They have the runaway greenhouse effect where their atmosphere is like 96% carbon dioxide. So here, what you see is almost all incoming shortwave radiation re-radiated back into the atmosphere. And that comes back down to the surface of Venus, making it really hot, 523 degrees Celsius. Okay, so let's talk about some natural causes to climate change, or how climate change, as a result of collecting all that climate data from the past, these are some of the natural reasons why our Earth has kind of gone through glacial and interglacial periods, or cooler or warmer times. One are plate movements or plate tectonics, moving major land masses. When land masses move closer or further away from the equator, that affects global climate. Okay, one example is Antarctica. Antarctica wasn't always completely covered in ice. It used to be a little further north and closer to South America, and ocean circulation, some of the warm tropical waters that move southward towards more southerly or high latitudes in the southern hemisphere would warm up Antarctica, and it was actually ice-free, and that was about 20 million years ago. But because of plate tectonics, Antarctica continued to move southward, and it altered ocean circulation, and then there was a circumpolar Antarctic current that cut Antarctica from all other warmer ocean currents and essentially covered it in ice. And the reason that affects global climate is because Antarctica is covered in ice, ice reflects out more solar radiation than land does. Like land, when solar radiation strikes land, it absorbs it, right? And it heats up, re-radiates it out, and it can get trapped in the atmosphere. Well, ice is kind of like a mirror, and it has really high albedo, and so when the solar radiation hits land that was formerly not covered in ice, hits that ice, a higher percentage of that solar radiation is going to be reflected directly back out into space, and the Earth loses on that solar radiation as a result. But again, this occurred 20 million years ago, and for the past 20 million years, there hasn't been much change in terms of plate tectonics. Remember, these are the scale of this change is in the hundreds of millions of years, because plates only move a couple centimeters a year. So if we're talking about the warming we've seen over the past 150 years, in 150 years, we've traveled, what, 300 centimeters westerly in America? That has very little effect in terms of our current situation. There are variations in our Earth's orbit. There are changes in eccentricity, obliquity, and precession. These scales are every 20 to 100,000. Eccentricity is the kind of waxing and waning of our orbit. Our orbit's elliptical. So every 100,000 years, about, our orbit becomes from low eccentricity, meaning that it's more circular, okay, to high eccentricity, which means more elliptical, okay. So on average, this alters the amount of solar radiation you receive in a year based on the flattening and expanding of our orbit, okay. But that goes from a maximum and a minimum every 100,000 years. We do have changes in our tilt or obliquity. It goes from 21.5 to 24.5 degrees. So if you imagine this, I just keep blocking everything. If you imagine this is our axis, and so our axis moves. Every 41,000 years goes from one end to another. Okay, and that affects how much solar radiation we receive, because more of the Earth will be facing the sun and more of it will be kind of facing away from the sun. And finally, there's precession. This is our Earth's wobble. I don't know if you ever played with a top, but with a spinning object, once you start spinning it, if it slows down a little bit, you'll start to notice that it begins to wobble. That's precession. And so we do have a little bit of a wobble in our axis as well, and that affects our climate. Other natural causes of the climate change, volcanic activity is one notable one. Volcanoes erupt massively, and they can dump a lot of aerosols in the atmosphere, and what that does, that kind of blankets the atmosphere with ash and small particles, and that actually reflects solar radiation out back to space, and that will lower global temperatures. These type of eruptions, ones that have a lot of aerosols involved, are usually short-lived. One notable example is in 1815, that was termed the year without summer, and that's because Mount Tambora erupted and blanketed the atmosphere with so much ash that in 1815, that year, it blocked out so much solar radiation that there was a huge decline in agricultural productivity as a result of that, and they had a very mild summer and caused mass famine. Okay. Another example, Mount St. Helens, that eruption was very big. It put a lot of ash and dust into the atmosphere. That had very little effect. It wasn't a big enough eruption. El Chinchon in Mexico in 1982 erupted a lot of sulfur dioxide gas, which combined with water vapor, and that produced sulfuric and acid particles. So there was acid rain as a result of this. And it remained up there for several years in the upper atmosphere. And those acid droplets reflected a lot of solar radiation back to space, and the lowered global temperature effect of this was about a 0.5 degree Celsius, just from one volcanic eruption. So here's a graph showing you time from 1973 to 1998, and this is incoming solar radiation, okay? And what you see is a big drop after El Chinchon erupted, but then everything kind of bounces back to normal after about a year, or half a year. And then here's another volcanic eruption, and then solar radiation is reduced because of that. So that's net solar radiation, okay? So volcanic eruptions actually lower global temperatures because they block the sun out. But other major eruptions, we're not talking about these kind of short-lived, one-time blow explosions, but sometimes giant fissures can just open up on continents, like Deccan traps or the Siberian traps, or the Columbia River Plateau eruptions. And that extensive volcanism can increase atmospheric CO2. So when you start changing the composition of the atmosphere, that has a longer effect on climate. Okay, and as a result, in the Cretaceous, that was one of the warmest times in Earth's history, and it was because of the extensive lava plateaus and volcanism that was occurring during that time. The sun itself is variable in terms of its output of solar radiation. Scientists haven't been able to detect a long-term variation in solar intensity, but there is a shorter-term one. It's every 11 years. There are these sunspot cycles. Sunspots are just huge magnetic storms on the sun, and they appear as little small dark spots, and they kind of reach a maximum every 11 years. So that cycle, 11-year cycle of kind of maximum sunspots, reduction in sunspots, that just cycle keeps happening every 11 years, right? Up and down, less and more solar intensity. So we've seen a trend over the past 150 years that our Earth is warming. So these cycles are too short to contribute to that or be a reason for our current state of warming. So here's a view of some of those sunspots. This is ultraviolet view of those magnetic storms that are occurring. Pretty crazy. All right, and then this is the kind of maximum and minimum waning and waxing of the sunspots through time. Okay, annual number of sunspots. Okay, and then let's turn to us. Let's point the finger directly at us. What's going on? We've been modifying the environment for thousands of years. Once we started building cities and domesticating animals, grazing land, and performing agriculture. So fire and overgrazing can change the landscape, and that can affect evaporation rates, reflectivity of the sun, even surface winds. But really the most important and drastic thing that we've been doing is altering the composition of the atmosphere. And that's by releasing a lot of carbon dioxide gas into the atmosphere. So shortwave radiation comes into Earth, and then when it's re-radiated back out, it gets trapped by greenhouse gases, and CO2 levels are the big reason for that. We've been adding carbon dioxide to the atmosphere because we've been burning fossil fuels. Okay, remember, a lot of the coal that we dig up and burn, which puts a lot of CO2 in the atmosphere, that's organic material. That's organic carbon material that's buried deep underground, has been out of the carbon cycle. Okay, so we're digging that out of the ground and burning it, and basically transferring buried carbon and transferring that back into our atmosphere, which eventually gets absorbed by our oceans. Okay, so we're completely throwing our carbon cycle out of whack by introducing really old carbon from the Paleozoic and introducing it into the atmosphere through burning of those fossil fuels. Okay. Also, deforestation is a problem because plants are a sink for carbon dioxide. They pull it out of the atmosphere. And so here's the seasonally corrected data for the monthly CO2 concentration since 1960. And clearly, we used to be at about 320 ppm. Now we're like 408 or 412 ppm is where we are today. So clearly upward trend. Okay, so we've had increased CO2 concentrations. Okay, there's a tropical deforestation as one of the problems. And now this is really one of the most important graphs here is we have carbon dioxide in parts per million on the y-axis from 160 ppm to 460. And this is years before today. So 0 is today. Okay, this book was written in 2015, so that's today, for example. But this climate record goes back all the way about 400,000 years. So this is the past 400,000 years of direct CO2 concentration of our atmosphere. Okay. And during these times in the past 400,000 years, we've gone from glacial to interglacial period, kind of like this cycle every 100,000 years, this orbital forcing climate change. Okay, so the Milankovitch cycles, those variations in our orbit, is largely what has caused our last kind of glacial to interglacial periods over the past 3.6 million years. Scientists can say that pretty confidently. And so what the rhythm, the natural climate rhythm has been over the past 3.6 million years is about every 100,000 years we go from high carbon dioxide, right? If we have more carbon dioxide in our atmosphere, that means it's warmer. The atmosphere is trapping more heat and our Earth is warmer. Sea levels are much higher, okay? And this correlates well with all the data we've collected from fossils and the stable isotopic data. Okay, and then when we go, then as carbon dioxide levels decrease to a minimum here, these are glacial periods. So here about, let's say, I don't know, what is this? This is 330,000 years ago, we were in a glacial period. And then we go back to a warm period, interglacial, glacial, interglacial, glacial, interglacial, and glacial. So that's been our kind of pattern back and forth every 100,000 years. Because of that orbital forcing, we go through these drastic changes in climate. And again, when we're talking about a glacial period, this is glaciers on continents, places covering places like Detroit, Wisconsin, through a lot of the Midwest, like continental glaciers just advancing in those areas. That's how cold it was. And so our modern day, we were just in a glacial period about 18,000 years ago, and then we've been kind of coming out of that, right? And we're kind of hitting this area here, which would be a classic interglacial period. But then what happens, humans are around, the Industrial Revolution, and now we've been pumping a lot of CO2 in the atmosphere. And this is where we are today, guys. We're at over 400 ppm today. So over the past 650,000 years, CO2 has never surpassed 300 ppm. And today we're at 415. Just let that sink in for a second. So the past 650 years, 650,000 years, 650,000 years, the Earth has never surpassed 300 ppm carbon dioxide in the atmosphere. Today we're at 412, I think, ppm. Okay, so we're way out of whack, way out of normal. Okay, so what's our atmosphere's response to all the CO2? Well, global temperatures have increased, okay, and global temperatures have increased about 0.8 degrees Celsius in the past century. This is direct data. Like you cannot, you know, refute this. This is collected data. We have gotten warmer, okay, and just to put that into perspective, the past 16 years, okay, so since 1850, all right. The warmest 16 years have occurred since 1995. Okay, and this book was written in 2015. So let's do the math here. That's 15. That's the past 20 years if we were in 2015. 16 of the warmest years since 1850. Okay, so that's over 165 years. 16 of those past 165 years have been the past 16 years have been the warmest of the since 1850. Okay, you're probably very confused, but anyways, it's been warm more recently. Okay, temperatures are expected to continue to increase in the future. All right, and that entirely depends on how much CO2 we're emitting into the atmosphere. This is undisputed data. This is how the global temperature change since 1880. Okay, so this is basically since we've been recording global temperatures. So we were here in 1880, today we're up here, and that's about 0.8 increase, 0.8 degrees Celsius globally. Okay, here's the decade by decade temperature trend. Okay, I'm sure you guys are very familiar with exponential growth, especially in the pandemic time like this. But look, every decade since 1950 has been warmer than the previous decade, and they're just continually getting warmer and warmer. So far, oh, we finished this decade. Yay. So here's 2020 finished, and this decade so far has been warmer than the 2000s. Okay. So each decade preceding it has been warmer. The areas that have seen the largest changes in temperature, mostly in the northern hemisphere and mostly on land. Okay, some areas here in the southern hemisphere have seen much higher temperatures than normal. So that's what's happening. That's where the heat is going. Now here, this is where there's debate. Okay, this is where scientists are currently debating. Forget about the debates that go on major news networks or cable news. Don't watch that stuff. It's not a controversy. This is occurring. Global temperatures are rising. What scientists are debating is how bad it's going to be. They're debating like what the future is going, how hot the future is going to be. So these are all different projections from different scenarios. If we do nothing, it's this red scenario here. So we'll have by 2100, which is in 80 years, about 3.5 degree increase in temperature. If we do some stuff and not much, we'll see about a 2.5 degree increase. And then if we do a lot of things, we're flattening the curve. Yay, right? And then we'll still see about 1.5 degrees of increased global temperatures because of all of what we already have done. Okay, even if we were to completely stop all CO2 emissions, we would still see an increase of about 0.5 degrees Celsius. A lot of damage has already been done. Okay, so there are other gases involved in global climate change. There's methane. Now methane is more effective or efficient at absorbing outgoing radiation, but it's just less abundant, so we don't focus on it as much. Nitrous oxides, another greenhouse gas. CFCs are a commercially produced chemical that depletes the ozone, so that's a big problem. But it really is a combined effect. So you have to take into account all of these greenhouse gases as a contributor to global warming. But CO2 is by far the single most important cause. Here are the concentrations of those other gases. Well, just methane and nitrous oxide since the Industrial Revolution. Okay, so here is their kind of standard natural concentrations. Industrial Revolution, pow, pow, right? Increase in concentrations. Now let's talk about aerosols. Aerosols influence the climate by kind of cooling it down temporarily. And what they are just tiny particles in the atmosphere, or drops of liquid, and they provide a cooling effect because they reflect the sunlight back into space. Okay, and so in contrast to aerosols cool down the Earth. Carbon dioxide will warm up the Earth, but the difference is carbon dioxide remains in the atmosphere for much longer time spans. And so it influences climate for decades, while as aerosols can be up in the atmosphere for just a few weeks. Okay, so most human-generated aerosols come from the burning of fossil fuels. Black carbon and that soot is emitted, and so that initially, let's show you a picture. Yeah, this is Shenzhou and Beijing in China, and these are heavy clouds and pollutants from coal burning power plants here. And so this is the aerosol index. These areas are covered in aerosols. So if you've been at these cities in China, they're very dark and gray because sunlight won't reach the surface here. So that has a temporary kind of cooling effect as a result of those aerosols. But long term, the CO2 being put in the atmosphere from those plants is going to warm it's going to warm the globe. So climate is very complex. It's dynamic. It's very hard to predict. So scientists have to consider a lot of different variables and factors. And some possible outcomes are feedback mechanisms. Okay, and what those are, they complicate predicting future climate change, and there are positive and negative feedback mechanisms. I'll talk about them both. Positive feedback mechanisms are when there's a change in the system and that change reinforces that initial change. It's often called the snowball effect. If you roll a snowball down a snow-covered hill, it'll get larger and larger and larger, right? So that's what they say when a problem's snowballing, it just gets bigger and bigger and worse and worse. So here's your example of a positive feedback mechanism. So say you have warmer waters, or you have warmer temperatures at high latitudes. That causes sea ice to melt. And that's replaced with lower albedo ocean. Remember, because sea ice will reflect more solar radiation out into space. And so if you have more ocean with lower albedo exposed to solar radiation, that increases solar radiation being absorbed, which increases temperature. And you can see how if then you have more increase of temperature, less sea ice, more solar radiation absorption, less sea ice, and you can see how that snowballs out of control. That's a positive feedback mechanism. So decline in ice cover, reduced reflectivity, increased absorption, warmer ocean, longer melt period, decline in ice cover, reduced reflectivity. You see how that just snowballs and snowballs out of control. Okay. A negative feedback mechanism is when the results, that initial change, are opposed. That the result opposes the initial change, and so it tends to offset. So an example here is that if we have global temperatures increasing, that increases evaporation, which leads to more cloud creation and cloud cover because there's more water vapor in the air. And that means that you have more clouds, that means more solar radiation is reflected back into space. And that, in effect, would lower global temperatures. Okay, so the reality is both these things are occurring at the same time. Yeah, global temperatures are increasing, causing more cloud cover and more water vapor in the air, right? That would lower global temperatures. But the sea ice positive reinforcement mechanism is also occurring at the same time. So you see, scientific modelers have to assign weights to the various positive feedback mechanisms and negative feedback mechanisms, assign values to them, like how important they are, how much they're affecting the climate, so that they can accurately model what will happen in the future. And that's why it's so difficult to do this. Okay. So here, this is a worthwhile link to click on. This is a study done by NASA, and NASA kind of pinpoints exactly what are the factors in terms of the last 150 years of global warming that have occurred. And I can't show you because I can't click out of this and continue the video, but do it. It shows you how all the natural factors we talked about, how that would have influenced our climate. And then it shows all the human factors. And it's pretty startling how the natural and human causes to climate change mirrors this black line is our actual temperature increase over the past 150 years. And it's because those models predict this. So we have no one else to blame but ourselves for this increase in global temperature. Okay, so let's talk about some of the consequences of global warming. Okay, the magnitude of temperature increase is not the same everywhere. We talked about that. The northern hemisphere is kind of getting a brunt of a lot of the warming. Precipitation changes will vary across the globe. Some places will receive more rain, some less, and so some places will experience drought or longer drought periods. We can nudge maybe those areas in California. They've been experiencing some pretty bad droughts and crazy brush fires and from their fire seasons. But one thing that'll affect all coastal communities is sea level rise. Sea level, this is undisputed, has already risen 25 centimeters since 1870. That's direct observation. Direct evidence. And so a lot of low-lying countries with gently sloping shorelines, which means the entire Atlantic coast of the U.S., they'll be affected by the rise in sea level. And so what this is driven by is two things. One, all the glaciers are melting. And so goodbye to glaciers, right? They're all melting. All that water is going back into the ocean. And in addition to that is the oceans are warming. And when the oceans are warming, water will thermally expand, and so that expansion will move onto land. Here are the projections for future sea level rise. Currently, it's only a couple millimeters per year, but that adds up over time. By 2100, here are the different projections. Worst case scenario, 2 meters. Okay, that's like almost 7 feet. Okay, so places places like South Florida, many places are only about 5 to 10 feet above sea level. Yeah, and that doesn't even count for the tides. Like, let's say there's a spring tide or a king tide or storm surge from a hurricane. That means these areas are going to be either completely inundated and flooded from the ocean by 2100, or just a hurricane coming through. That storm surge will push that water further inland and flood everything. Okay, the lowest projections based on if we act now would be only about a 0.2 meter increase in sea level. And then this here is the observed. That's undisputed. These are just projections into the future. Okay, so this is what the shorelines will look like. Okay, shorelines will shift. Okay. Let's take a look at what Florida would look like. This is beyond 2100. This is plus 6 meters of sea level rise. So this is 3 times what I showed you in that 2100 projection. But the reason why I show it is just because Florida is a low-lying state, and essentially, I was born in Fort Lauderdale. That will be gone. Okay, all of Miami, the Keys, okay, Fort Myers, a lot of Clearwater, a lot of Jacksonville. This whole area will become, the St. Johns River become like a saltwater estuary. Cape Canaveral, gone. Okay, we're still fine in Orlando. We're at like, our drive to the coast will be shorter, I guess, but that's pretty bad. Look, Florida basically loses almost like 25% of its land as a result of it. Tallahassee will be a coastal city. Oh yeah, that's what it'll look like here. This is what the future holds for Florida. Sea level rise. Wow. All right, some other consequences of global warming is the changing Arctic. Our poles are going to change drastically. Arctic sea ice has been in decline for a while. Since 1979, it's about 13% decline. There's also been a decline in permafrost. This is one of the examples of positive feedback. Permafrost is ground that's permanently frozen throughout the year. They might have maybe a couple centimeters of an active layer only in the summer, but for the most part, it's frozen solid. And what happens is, if that stuff starts thawing because of warming temperatures, there's a lot of trapped methane underground and CO2 in that permafrost. And so you see that's a positive mechanism. Warmer temperatures, more greenhouse gases emitted, leading to more temperatures, leading to more permafrost being thawed, leading to more greenhouse gases being emitted. So that's a big problem. Here's the decline in sea ice volume since 1979. Okay, downward trend. Here's some satellite images of the decline in sea ice. Okay, so that's where polar bears live. What's going to happen to those polar bears? Right, they're going to lose a lot of their habitat. Okay, here is the 2015 minimum. This was 1981 to 2010 median minimum. Okay, so average minimum ice, so that has decreased drastically since 1978. Again, this is the same graph, just same data, just different graph. So what does that mean for the poor polar bears? Yeah, look at that. Where's the Sarah McLachlan music now? You gonna adopt a polar bear or something? No, this is their dwindling environment. They're gonna get real skinny because they can't find food. Here's a time-lapse photography of a glacier. Here it is in 1921, and here it is in 2009. Really? Direct evidence of glaciers completely disappearing. Our landscape is changing. So in the northern hemispheres, what we're also seeing is changing or predicted increase in plant growth. So different vegetation is going to start moving further northward because of the expanded warmth and thawing permafrost. So these landscapes are changing drastically. You can talk to biologists, and they can talk to you about how different species of trees and shrubs and plants are all moving further northward. And all these cold plant species are dying off. In Siberia, they have these lakes, and they're releasing a lot of methane bubbles. In my media page on Canvas, watch the documentary, National Geographic documentary I posted. They show scientists going to these Siberian lakes, and they can actually light these. The bubbles are kind of coming off of it because of that thawing permafrost, and these lakes can light on fire, which is pretty crazy. You can also YouTube it. Other consequences of global warming, the ocean is going to become more acidic, and that's because the ocean largely absorbs a lot of the excess carbon dioxide that's in our atmosphere. And what happens is it dissolves in the ocean, and so the ocean becomes more acidic. Distilled water is at 7. Most ocean water is around here, okay? And so if you add more carbon dioxide, that creates carbonic acid and makes the ocean more acidic. And that will contribute to organisms ocean organisms not able to create their shells out of calcium carbonate because the ocean is more acidic. And warmer oceans lead to coral bleaching, is what you see here. Looks like someone poured bleach on this coral. That's not the case. If waters are too warm, or if they're too acidic, this can kill the zooxanthellae that live within the coral polyps, and they get expelled, and the coral loses its color, and then the coral polyps die, and that's it. This is just a remnant of what used to be a living organism. And another possible consequence is changing in ocean circulation. A lot of the areas in Northern Europe, Norway, Sweden, Denmark, and the UK, these places are livable despite being at really high latitudes. Look at the comparison. They're like in that latitude is the same as kind of northern Russia, which is essentially unlivable. And also, if you go into the U.S., that's like northern Canada, and only the Inuits live in these regions. So very sparsely populated, terrible weather. The reason why these areas are inhabitable is because of the Gulf Stream. The Gulf Stream brings a lot of warm tropical waters across the Atlantic and into this area of Europe. Okay, and then as it goes northward, it cools down and then it sinks, and then it sinks here and it becomes part of this three-dimensional circulation in the ocean. But what will happen is if the oceans warm up too much, that warm water from the tropics might not sink in this area. So it might kind of just come back down and not sink here, and then now ocean circulation's changed, and this area might see global cooling as a result of global warming, which is pretty crazy. You could see a cooling of 1 to 3 degrees in the UK and Scandinavia, while the rest of Europe sees warming, which is pretty freaky. Okay, so why should you believe scientists? Well, because they go through this entire process called the peer review process. Essentially what they do is they work, collect data, they go through the entire scientific method, and we've talked about that before, and they draft a manuscript. Really hard work. Their scientific studies based on data collection or experimentation, and they put it together and publish it. And when they publish it, or attempt to publish it, they send their manuscript to what we call the reviewers. These are the gatekeepers. These are all these experts that have their PhDs. Think of Dr. Fauci, right? These guys will review your work to its accuracy and make sure you're not overstating anything and not obfuscating something else, or making sure you're doing good work. Okay, that's why it's called peer review, because these are your peers and they're reviewing your work. And only after they've accepted your work and they know that it's not, falsified or come up with bad conclusions, then you're allowed to edit and publish that. And once it's published in a scientific journal, which is scientific journals are kind of the highest level of publishing, then that's kind of given out to the scientific community to read at large, and then it's kind of essentially translated to the media and then passed on to everyone. And so what authors receive is just attention and reputation. And there is no kind of monetary incentive for any type of results for scientists. They're just trying to get the truth out there and or as best they can represent it with the data that they've collected. And so there's no industry behind what's good news or bad news. They're just reporting what data they've collected and the results that they've found. Okay, so here's a little joke. Most scientists have to go through this new peer review process. Here are the peers tearing up your work. It's really hard to publish in these type of papers. And so here's a peer-reviewed paper that was published. You can click on this. This is a scientist that went through over like 10,000 papers that are being published actively in scientific journals, meaning that these are the papers that are going through that peer review process. And what they found was there's a consensus on consensus. And of all, it's something like 96% of climate scientists believe that the recent global warming we've seen is human caused. Okay, so these are the experts, and in times like these, we really need to lean on experts and listen to smart people. Okay, people who've spent time and done their homework and done the hard work, rather than just talking heads and, you know, people on the news, right? Because it's really unfair. They'll have like Bill Nye the Science Guy, right? Who's like, yeah, global warming's real and it's a big problem. And then they'll be like, oh, here's this other guy, right? And it gives it like a false sense of equivalency, like that there's supposed to be a controversy if there's one guy saying yes and one guy saying no. And they're like, this guy's a scientist and this guy's a paid advocate for an advertising company who is doesn't know anything about science and is going to contradict everything. Right. So here are different agencies that just agree with the paper. And if you ask the public, if you ask 96% of climate scientists that are actively publishing, do you think human activity is a significant contributing factor to global mean increase in temperatures? 97% of them say yes. When you go down the list, these are non-publishers and non-climatologists say 90%. Climatologists, about 87% say yes. Active publishers, any scientific publishers in any topic, it's about 87%. Non-publishing, non-climatologists, they're up to 78%. But if you ask the general public, that's about 58% say yes. And that is, that is a victory. That's media control kind of creating a controversy. And they've also politicized it, really. Sadly, we're kind of in a very tribal political current situation. And when one party largely denies that there's human-induced climate change, a lot of people identify with that party, and they're just going to parrot what their party leaders are going to say without looking at any of the evidence, which is a shame. And that's why when you ask the general public, only about 58% of people believe that we're responsible for the recent increase in global temperatures. And there's an entire industry behind that. There's an entire industry that wants that to happen. The fossil fuel industry pays advertising companies to bring doubt to the American people and to make it seem like it's a controversy. Among scientists, it's clearly not a controversy. The vast majority of scientists agree that we're responsible for the global temperature. What they're focused on are the real problems. They're focused on how much is sea level going to rise? How is our climate going to change? How is this going to affect our future crop yields and stuff like that, the real problems.